I'm Kieron Salter. I am the founder and current managing director of KW Special Projects. I say current because I'm trying to make myself obsolete. I'm trying to bring some other people in to make me less busy. Special Projects is a spin-out company from a previous company I owned, which is still in operation, called KW Motorsport. So we have a strong motorsport background, and so there's a bit of motorsport theme in some of the things I'm going to show you here. But what I'm going to do is Sophie's presentation. There's a little bit of crossover actually with some of the stuff I've got later on, which is quite interesting. But Sophie's stuff was very much about fundamental research into additive and digital deposition technologies. I'm going to show you some of the applications and some of the things we do where we help our customers realise those as actual manufacturing processes. So Special Projects is fundamentally a research and development organisation. We both conduct funded R&D for our customers and also internal R&D that we fund ourselves. And our skill sets, as it shows there, is mechanical, electrical, control systems, automation, and software. And we're not really very sector specific. We kind of focus on some core technologies of advanced materials and lightweight structures and control systems. And then we use systems integration to bring all those things together. But the sectors that we cover are quite broad, but we can categorise it a little bit with sort of automotive and mobility, performance sports, and digital manufacturing, which is some of the examples I'm going to show you today. Fortunate enough to have a pretty good range of high-level customers, which when you're trying to fund R&D, this is essential because they also have the real-world applications, the things that the problems you're trying to solve. There's some motorsport ones there. There's some perhaps that are not so obvious. For example, what we were doing with Nike. Well, that was actually a digital manufacturing project. So we're helping them with their manufacturing process, not with their sports equipment. Yet with English Institute of Sport, we're actually helping them with sports equipment because we're doing R&D and development into how they make their sports better. And you'll learn a bit more about that later. But our additive manufacturing side, we have internally a suite of Stratasys FDM machines, which we use for both our own projects and also as a service to our customers. A lot of the work that we do is how we exploit additive as a useful tool for those customers. So it's the classic rapid prototyping, but also end-use parts, moulds and tooling, replacement parts, and complex jigs and fixtures. It's one that people overlook quite a lot, is the ability to create quick and easy complex jigs and fixtures for inspection or for assembly. Or for complex assembly tools. And then obsolescence management, which I've got an example of later as well. So the classic example of rapid prototyping is what we come from, the tradition of sort of additive manufacturing. Motorsports are a great opportunity for doing rapid prototyping. It's not really rapid prototyping in motorsport, it's actually rapid manufacturing of parts we actually use. But they're relatively low volumes. It's very fast cycle times in research and development, and we can sustain a little bit higher cost than most of industry. So actually it's a great playground for a lot of additive technology. And I'll run through this one quite quickly because I've actually done a much bigger presentation about the whole project before. But essentially we were tasked with a problem of remanufacturing a complete door hinge architecture for a Le Mans car, which you just saw in the previous picture. And the lead times were incredibly short. It was about 6 weeks to both design it, manufacture it, qualify it, validate it, and homologate for racing. And so we mitigated a lot of the problems and the risks in that by using additive. So we used our internal FDM capability to manufacture prototypes, for example, which allowed us to do quick kinematic analysis of essentially the finished components, but just not manufactured in the intended material. So it is manufactured in plastics, but it allowed us to do full kinematic analysis, allowed us to get the driver in the car, make sure that the door opened and closed in the way that was expected. But what surprised us at the time, because we were expecting to make these door hinges in conventional CNC machined steel, was that the best solution available to us was to use metal laser sintering and using titanium. And that was because turns out we couldn't even source the billet material for the CNC machining in the lead times that we needed to manufacture these parts. So we looked at additive, we looked at titanium, and we ended up making a part, and this doesn't happen very often in the world of additive manufacturing, but we ended up making a part that was cheaper, lighter, and quicker, and also stiffer. So we got all the wins by making an additive part. And the one that surprises everybody is that it was cheaper. But to CNC machine that in a low volume, a complex part, you can see it's fairly complex geometry, was just too expensive and took too long. But that's not all we use FDM for internally. We use it for composite tooling. And again, it's about rapid manufacturing. And this is really what I call digital tooling. So we print each tool for each composite part that we make individually. That part then gets consumed in the tooling process, and to make another part, we need to make another tool. So we print the composite tool on the left. We then wrap it in carbon fibre. We then wash away the soluble composite tool, and we end up with a carbon fibre shell of the desired geometry. Now that's basically investment casting for composites. And actually, the costs, again, in producing this compared to hard tooling for manufacturing this is significantly cheaper. So this is a process, again, that's not only disrupting the way that we used to make things and allows us to make things more rapidly and more complex, but it's also cheaper. And actually, in the world of Formula One, or in perhaps even medical, where you don't want to make thousands of parts all the same, you want to have that digital tooling ability that you print on demand, the features and the size of the tool that you want to make the parts. And then you consume that tool in the process, and when you come to make your next ones, you need another one. So for Formula One, that's great, because we're constantly redeveloping and re-engineering the parts. And in fact, I think last year we made about 3,500 parts just for the motorsport industry using that process. But there's also obsolescence. So this is a case where we're looking at projects or assets that perhaps don't even have any CAD data at all, let alone spare parts to repair them with. And this was a project we worked with a client. It was a 1926 Amel car. He had the car, he had some photographs, and he had some broken bits, and he wanted some replacement parts for a gearbox. So we took the components that he had, and we scanned them. That's not actually one of them, but it's an example. We scanned them using our Creaform scanning technology, and we reverse engineered, essentially, as we're all familiar with, the components that we needed to manufacture. So we put them into CAD, because you can't make anything in the additive manufacturing world without a digital asset. I think a lot of people overlook that. So you've either got to already have some CAD data, or you've got to make some. So from our digital asset, we're able to do the other complex things that you can do within your CAD geometry. So you can look at the kinematics and the analysis and design the part. And then we're able to print a prototype of the part so that we could test it in the car and actually validate not only that it worked, but it was to the customer's liking, and it's the geometry fitted, and aesthetically he was happy with it. And then we're able to go straight to casting using another type of additive manufacturing process where we're printing the sand cast molds and making a low volume production run, or low volume run of one or two parts at very low cost for the customer. Again, this is an environment where, when I say low cost, the customer can sustain a much higher price per part than you could in the automotive world when you're making thousands of them. But this was a really very cost-effective and realistic solution to the customer to achieve something that he couldn't achieve any other way. So that was the finished gearbox part that we manufactured in casting. But for me, additive manufacturing is just a small part of what we as a business are focused on, which is digital manufacturing. And that's the bit that Sophie was talking about with the industrial inkjet. And actually, KW Special Projects was formed back in 2012 when I took my motorsport understanding of lightweighting and composites, met with a customer who was racing in the motorsport environment, who had a real world problem in his day business, which was industrial inkjet. I didn't know anything about industrial inkjet or the opportunities at the time, but we brought together motorsport technology and his problems in industrial inkjet, which were about making machines, and we solved a number of his problems using lightweighting and composites. And that's what we call horizontal innovation, where we're breaking down the silos of different industries and different sectors, and we're saying something that works in this sector, something that I know here that I'm an expert in composites because of motorsport, I can apply to an industrial application somewhere else. And that started KW Special Projects in 2012 when we built this very large print engine. So this is for an industrial inkjet application using the kind of technology that Sophie was talking about. This has 120 print heads in it. The customer's challenge was that using traditional methods of making in steel and aluminium plate, it was very heavy, it was subjective to thermal expansion, it was difficult to machine and make accurate, and it was also a very difficult thing to package. Using composites, we're able to mould very complex shapes. It was stiffer, it was lighter, and because it was carbon fibre, it had virtually zero thermal expansion, coefficient of thermal expansion. So it managed the the accuracy and the management of the print heads really well, which was a byproduct that that the customer didn't necessarily expect of that product. But again, it was a perfect example of a horizontal innovation. Where that led to was us establishing digital manufacturing in terms of application. So we now take a customer's manufacturing requirement, and we look at technologies like the ones that Additive Scientifically are developing in fundamental research, and we build real machines that can apply that solution. And now we have internally, we have a lab printer that allows you to basically parameterize a number of different print heads, materials, and trial your application. Customers that have bought one of those then move on to a pilot line, which is very similar to the printer that Sophie showed you in a previous presentation. That's our product, that's a KWSP product. It's full safety systems, it's fully automated, and it's configurable. So our clients can install any combination of print heads. They can install a hybrid solution. They can install their own fluid control systems or use the ones that we have. And they can build basically a pilot line of what they intend to be as a manufacturing line using digital manufacturing process for the future. And by digital manufacturing, really what that means to me is driving your manufacturing via software. So trying to drive zero tooling and essentially software in and parts out, which is what we're all familiar with additive 3D printing. You send your CAD file, you get your part out, you don't change anything else except perhaps the material. So the dream is to have pilot lines that can allow people to develop their digital manufacturing solution. But that's led into some other projects, some of which have been funded by Horizon 2020, some by Innovate UK. One of them is it's not really 3D printing, this is more 2.5D, but again, it's using a version of material deposition. It's not inkjet, it actually deposits a powder. But this is a printer that allows hard of sight to print Braille on demand. Believe it or not, you can't do that at the moment. The Braille industry for the consumer is still in the world of the typewriter, and we're all moved on to Amazon Alexas and printers. So this is a consumer product. When the project is finished later this year, we will have a printer similar to the ones that you see on the left there. It will be a consumer desktop product that will allow people to print directly from the web, directly for books, from a scanner, convert via text into Braille on demand. And the real nice thing about that is not only can you print Braille, which is in the traditional form, but you can actually start to print pictures and other forms that children can start to learn from as well. So that's a really nice social engineering project. We've also got a project where we're developing a completely new way of manufacturing foot orthotics. So many foot orthotics are already made using, some of them made using additive manufacturing, but the limitations are it's a very slow process, it's still quite expensive. The vision of this project is to bring together a complete digital loop of how you go from consultation through to automation of the CAD, through prescription, through to on-site manufacturing on demand. So Vision Express for foot orthotics. So we aim to be able to print a full set of foot orthotics per customer in less than 2 hours. At the moment, it's several weeks. That's another Innovate UK funded project with our partners Podfo. And recently, we've just been awarded a project to look at how we use digital deposition in the manufacturing of battery cells. So batteries are, through the Faraday Challenge, an enormous subject of attention at the moment. Electric vehicles, home storage, static storage. We're going to need to make a lot of batteries in the future, and we need to improve the way we make batteries. Now, battery manufacturing is still analog. It's using a very old roll-to-roll printing process. Some of the problems with quality in manufacturing of cells is down to the control of that analog process, and we think we can improve that by making it a digital manufacturing process using, again, industrial inkjet, but we are challenged by some of the things that Sophie mentioned, like viscosity, and for that purpose we have a completely new type of print head that we intend to use to deposit the viscous graphite materials and other materials that will be used to make the anodes. So that's a really exciting project just about to start. I don't know how much time I've got left, but perfect. So it's not just about the manufacturing side, though. I talked about the digital asset. Now we need to look at the digital bit that drives our manufacturing process, and not only drives it, but controls it. So we're very interested in the whole Internet of Things and how you connect your machines and how you get data from your machines to improve your manufacturing process, how you use the data from the machines to predict maintenance requirements. So all of our machines, the pilot line that I showed you just now, for example, is Industry 4 compatible. They're connected. They're able to be connected to the cloud or to remote monitoring systems. And so we're starting to close the loop. And an example of that, and I mentioned at the beginning, we're quite diverse in the type of projects that we work on, and we're not sector specific. We do quite a bit of work in performance sport, not just motorsport, but athlete sport. One of our projects is building a wind tunnel for performance cycling, and this is a consumer wind tunnel at the moment. The first one's being commissioned at the moment in Evesham for Halford's own Boardman bikes, and there will be a Boardman Performance Centre in Evesham in a few months' time where you as a consumer can go in and do real live wind tunnel testing to understand how you as an athlete have an impact on the drag of your bike. But when we designed that wind tunnel as a machine, we want to be able to remotely operate it or maintain it, and we hope to have several of these around the world. We don't want to be sending field technicians out on a regular basis looking. We want to collect the data, interrogate that data, and be able to predict maintenance scenarios, and also help our customers remotely with that. So that's the benefit of being connected, and the benefit of being Industry 4, is that you take all the sensor activity that you've got within your machine, that's basically a machine, and you use that data to predict scenarios. So the big one for us is the fan that drives the wind in the wind tunnel. There's some big motors in it and there are bearings, and we don't want to find out that it's broken and then have to go and replace it and the tunnel will be down for several days or maybe even weeks, particularly if there's long lead items involved. We want to be able to predict that, and actually you can predict that. This is from a wind turbine example, actually exactly the same kind of problem, and you can, if you have enough data, you can very easily predict a failure event, and you can do something about it way ahead of schedule, way ahead of it actually happening, and you can plan the maintenance for that will keep the machine running 24 hours a day, 7 days a week. So that's connecting the machines to the internet and then using that data to have an impact on the outcome. So Sophie also mentioned about pharmaceuticals and FDA. One of the very first machines we built was actually a fully FDA approved machine. We didn't know anything about FDA at the time, we had to learn all about it. But this is a fully qualified, validated, signed off by TÜV FDA industrial inkjet printing machine for a real pharmaceutical or clinical application. That's not the reason I put that one in there. I put that one in there because what happened to it next is it went into a manufacturing cell, which was fully automated and connected in the way that I just talked about the wind tunnel project. So once we've got industrial inkjet manufacturing as a solution for how you can make things, and you can then start to connect it into an automated process, and you can start to scale up and industrialize your additive manufacturing solutions, then you've really got to start to have something useful that OEMs and customers can find useful in their manufacturing. They can build a proper, flexible digital manufacturing solution. So that's actually our machine up and running. It's been running now for several years. As I say, FDA approved, integrated with robotic control. And the reason that's exciting is because our vision is to actually scale up industrial manufacturing of additive and digital manufacturing in general. And we've just announced a project over at Silverstone, which is near where we're based, through the Silverstone Technology Cluster, where we intend to create a true digital manufacturing centre, where we can really industrialise and scale up how you use additive as part of the manufacturing process. Because it's not just about having a 3D printer or even a large-scale 3D printer. It's how you automate that through robots and, courtesy of Stratasys, these ideas of a factory of the future where you can print, and we've seen this morning as well, printing car chassis, but you can start to integrate all these manufacturing processes, whether it's industrial inkjet, whether it's metal laser sintering, whether it's FDM, robotics, control, Industry 4. We want to build a facility at Silverstone that allows us to scale up and provide our customers with pilot lines and discrete manufacturing of metal parts that are fully finished, not just printing of metal parts. So, as I say, industrial manufacturing using additive, not just the low volume, high value stuff that we see at the moment. That's a £10 million project that we hope to be fully signed off and committed to within the next few months. To finish, I mentioned again at the beginning about English Institute of Sport and R&D. This is a clue to a presentation I might be able to give in the future when we're free to speak about this more. But again, this is a real world application of how we had a significant impact on what was the most successful Winter Olympics for the British skeleton ever. And there was a significant amount of digital manufacturing and additive manufacturing invested in that 3-year project. Thank you.